Welcome students. Let us start chapter 8 Gravitation. First we will see topic 8.1, that is introduction about gravitation. See, the history of gravitation starts from very ancient days, from when humans started observing that there is a tendency of every material to be attracted towards earth. After this, human observed all the celestial bodies like moon, sun, planets, stars and so on. And there we observed that everything is revolving around earth. And from that observation, 2000 years ago, Ptolemy was the first to give a model for the planetary motion. The model that he gave is known as geocentric model, because in this model he suggested that sun, moon, planets and all celestial objects are revolving around the earth. Let me show you a figure of it. Here is the figure of Ptolemy's geocentric model. You can see here at the center is earth. This is moon, Mercury, Venus, sun, Mars, Jupiter, Saturn and all other stars. All are revolving around earth. That's why this model is known as geocentric model. Later on, after 400 years of this model, Indian astronomers also gave somewhat similar type of model, that means geocentric model. But after this, in 5th century AD, Aryabhatta, the Indian astronomer, gave a heliocentric model where sun was at the center and all the planets and all other celestial bodies were revolving around sun. Then nearly 1000 years later, a Polish monk named Nicholas Copernicus, he gave a definite model for planets moving in circles around fixed central sun. Means Copernicus gave the same heliocentric model that was given by Aryabhatta, but that was after 1000 years later. But unfortunately, the church discredited his theory. In fact, Galileo supported him. Let me show you a heliocentric model where sun is at the center. As you can see here, this is sun at the center and all the planets, Mercury, Venus, Earth and Moon, Mars, Jupiter, Saturn and stars, all are moving around sun in circles. This is the similar model that we use nowadays, only the difference is of orbits. Here, as per Copernicus, the orbits are circular, but now we know that orbits are elliptical. Now, Tycho Brahe, in the same time of Galileo almost, from Denmark, spent his entire life in observing and recording the motion of planets with naked eyes. Means he observed all the planets throughout his life and recorded all the observations. Then after, all of his compiled data were analyzed by his assistant Johannes Kepler, who gave 3 laws from this data, which was named as Keplers Law. Thus, from Tycho Brahe's observations, Kepler derived 3 laws which are known as Keplers Law. Now let us see topic 8.2, Kepler's laws. Here first we will see law of orbits. Now, before learning about laws of orbits, you must understand how to draw an ellipse, how to draw an elliptical shape. For that, let me show you a small video. And here it is. Look, first of all, draw a horizontal line, then a vertical line, and choose some 2 points like F1 and at the same distance from the center another point F2. Now take two pins and pierce them on points F1 and F2. Also take a closed string and take a pen, put it through this closed string, keeping the string taut, and now move the pen round in a manner that the string remains taut. So that creates a shape which is known as ellipse, or say elliptical shape. Here is that ellipse, and these two centers are known as foci of this ellipse. There are always two foci of an ellipse. One more thing, this is known as major axis and this one is known as minor axis. Okay. Now coming back to our point, here we were about to discuss Kepler's first law, that is law of orbits. Now here is the statement: all planets move in elliptical orbits with the sun situated at one of the foci of the ellipse. For this, see this figure. Here is sun and here is the orbit of any planet. Right? You can see the orbit of planet is elliptical. Now sun is at either S or either S dash. Here S and S dash are foci of this elliptical shape. Alright. So Kepler said that all the planets move in elliptical orbit, keeping the sun at one of its foci. And you can see here that sun is situated at the first foci. Here you can see that Kepler's first law is different than the statement given by Copernicus. Copernicus said that all the orbits of planet is circular in shape, whereas Kepler says that it is elliptical in shape. Now, one more important thing about this elliptical shape. This PA is known as major axis. So, the total distance of major axis is taken as 2a and the half of it, that means a, which is PA by 2, is known as semi-major axis. This is very important. A, that is known as semi-major axis, means from the center to one of the major end is known as semi-major axis. The same way BC is known as minor axis and its distance is taken as 2b. Now half of this distance is known as semi-minor axis. So small b, that is BC by 2, is known as semi-minor axis. In short, from this center to A or to P is known as semi-major axis and from this center to B or to C is known as semi-minor axis. Now let us see second law of Kepler, that is law of areas. The statement is like this: the line that joins any planet to the sun sweeps equal area in equal interval of time. Let me explain this with this figure here. You can see here is a planet moving in a elliptical shape and here at one of its foci this is sun, right? Now the line joining sun and planet is this one, SP. So when this planet moves on this orbit, the line joining sun and planet sweeps some area. You can see this is the area swept by the line joining sun and planet, that is this delta A. Now if the planet is here at point Q and it travels a distance from Q to Q dash, then here the line joining planet and sun sweeps a area delta A dash. You can see this is the area delta A dash. Also, let us assume that the time taken by the planet to move from P to P dash is delta t, and the same way the time taken by the planet to move from Q to Q dash is, let us say, delta t dash. Now here Kepler says that if the time interval delta t and delta t dash are same, then the area swept by the line which is joining the planet and the sun will be also same. That means area delta A and delta A dash will be also same. Means the line that joins planet and sun sweeps same area in same time interval. Here from this we can also say that delta A upon delta T will be equal to delta A dash upon delta T dash, and this is going to be constant. Now students, this delta A upon delta T, or say delta A dash upon delta T, is a very important physical quantity. This is known as aerial velocity. Yes, it is known as aerial velocity, and we can see that this aerial velocity is remaining constant. So here from Kepler's second law we are getting that the planet's aerial velocity always remains constant. This was just explanation of Kepler's second law, but we can also prove Kepler's second law by the use of conservation of angular momentum. So let us do that. First of all, see that here the area of triangle PSP dash, look here, PSP dash triangle. So the area of this triangle PSP dash is given by delta A, right? Now area of any triangle is always equal to 1 by 2 base into height. Now here in the figure, base is this one PP dash and height is this one, that is R, right? So I can write the base, that is PP dash, and height, that is R. Now this PP dash is the distance travelled by this planet with a velocity v in time delta t. So distance is equal to velocity into time. So at the place of PP dash I can write velocity v into time delta t, and the remaining is R. So now I can write delta A upon delta t, that will be equal to 1 by 2 v into R. Now let me multiply and divide this equation with m. So I will get delta A upon delta t as mvr divided by 2m. But this mvr is angular momentum L upon 2m. Here there is no external torque on the planet. So angular momentum L is constant, right? And m is obviously constant. So we can write that delta A upon delta t itself is constant. Delta A upon delta t is constant. You know that delta A upon delta t is aerial velocity. So I can write aerial velocity is constant. This is nothing but the expression of Kepler's second law, which suggests that the line joining planet and sun always sweeps same area in same time interval. That means the aerial velocity of a planet is always constant, right? Now let us see Kepler's third law, law of periods. Let us see its statement. Here it is. The square of the time period of revolution of a planet is proportional to the cube of the semi-major axis of the ellipse traced out by the planet. Now let me explain this with this figure. Here it is. You can see this is the elliptical orbit of this planet, and here is the sun at one of the foci. This is capital T, which is the time period of revolution of this planet on this orbit, and this is small a, that is the semi-major axis of the ellipse traced by this planet. This is semi-major axis A. So now as per the third law of Kepler, the square of the time period of revolution is proportional to the cube of semi-major axis. That means here we can write that T square, that is the square of the time period, is proportional to the cube of semi-major axis, that means A cube. Obviously here we can put some constant, so I can write T square is equal to Q A cube, where Q is just a proportionality constant. Okay, Q is a constant. So from this equation you can also write that Q will be equal to T square upon A cube, and that is going to be constant. Now this you can check in this table given below. Look, here A is semi-major axis in units of 10 raised to 10 meter. See this. Here the value of A is given, where you have to consider the values with 10 raised to 10 meter, right? Then capital T, that is time period of revolution of the planet in years. See this. This is the values of T which you have to consider in years. All the values are in year. See this. For Earth, the time period is 1 year. Then Q. Q is a quotient, that means a constant, and that is equal to T square by A cube. It is in units of 10 raised to minus 34 year square per meter cube. The value of Q here is in 10 raised to minus 34 year square per meter cube. Now these are all planets: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune and Pluto. These are the values of semi-major axis of these planets, and these are all the values of periodic time of these planets. And this is Q. This Q is the ratio of T square upon A cube for every planet. Now you see the values. Here for Mercury it is 2.95, then 3.00, then 2.96, 2.98, 3.01, 2.98, 2.98, 2.99 and 2.99. You can see the value of Q for every planet is almost same. It is almost same. That means T square upon A cube is constant. So this is the proof of Kepler's third law, that is law of period, which says that T square upon A cube is always constant, or we can say that T square is proportional to A cube always, right?